Hello everyone again and welcome to this particular video, and in here we're going to be exploring the relationship between pressure and molecular speeds of various gases, specifically looking at ideal gases that are inert and don't react with other gases. So the bell work here is that you should be able to state the kinetic model of gas assumptions, and these assumptions will then lead us into exploring the root mean square speed of molecules, and this is going to be incorporated into elastic collisions, which mainly focuses on momentum of molecules, and this will be integrated into the time interval and molecules in a volume, where we're going to be introducing the Avogadro's constant, and all this will then lead into finally concluding formula for the root mean square speed of various gases when incorporating pressure into this particular model. So the assumptions first for the kinetic model of gases are actually three, and these three includes first focusing on a container, and we have two gases. Both of them are not reactive, therefore this behavior is mainly focusing on an ideal gas. We first have to create an assumption that the random motion is made by gas molecules with a specific mass, which is represented as m. And then the second assumption that you have to take into consideration is that since molecules diameter is smaller than the average distance traveled between collisions with other molecules, this actually then leads us to the conclusion that the elastic collision with other molecules is a form of interaction when these two molecules are not reacting to each other. So this elastic collision then leads us to the idea of momentum created in this scenario. So big takeaway is that the assumption is that the diameter of a particular molecule is way smaller than the distance between the two molecules that are in a specific space or volume. So the third assumption here and final one is the introduction of kinetic energy that is created when a specific particle is moving in a specific space, and this energy is actually, well, we assume at first to be half mv squared based on physics, and this will then be applied into small molecules and mainly gases. So let's focus on assumption 3, where we are going to look at the contribution to energy of gas, that is the kinetic energy on molecules. And in here we express this to be kinetic energy to be half mv squared, and this actually our goal for this video is to derive the formula that shows the direct relationship, don't forget that, between pressure and the molecular speed. And this almighty, I call it, formula is represented as P, which is pressure, to be multiplied by the volume total of that particular area where all the gases are contained in, and this is equal to 1/3, which is of the number of moles, which is represented as n, multiplied by the molar mass of the gas in question, and finally C is represented as the root mean square speed of the specific gases. This takes into consideration the average of the square of those particular speeds of the individual molecules, and we're not talking about the one dimension, we are talking about including the 3 dimensions. That is where the 1/3 comes into play. So let's look at this in terms of actually deriving that particular formula, which shows the direct relationship between pressure and the root mean square speed of molecules. So first off, looking at deriving, in here we have this formula, which is our main goal at the end, and seeing this particular goal established, first we need to look at C. How do we determine C? based on the statement which says that c is the root mean square speed of the molecules, we need to take note that c is equal to the average or the square root of the average speed squares of the individual molecules in that particular container, where v is the speed of the molecules and those little sharp brackets or edge brackets represents the mean. So how do you determine c? To determine c mathematically, what you do first is to measure the individual molecule speeds, which is the v. So once you do that, the unit of course is the standard unit, which is meters per second. And then once you take the individual molecular speed measurements, what you do is you apply the square to the individual molecule speeds that were measured. And once you have determined that, then the next is to take the average of all the square speeds that were performed, and the average of these will be incorporated into being able to take the final step, which is performing the root of that particular average mean squared of that particular speeds. And once you're able to do that, then you've determined a specific value which truly represents that particular root mean square speed of that particular molecules in a container. So looking at that and moving into how we are going to incorporate the next necessary variable in here is considering elastic collision. And elastic collision is a derived relationship with momentum, and in momentum we notice in here that we have to consider not only the mass but also the velocity of that particular gas particle. So looking at the coordinates here, we have this direction to be represented as x, which is a positive direction, and we have a container which has a specific particle, and this particle, or we call it molecule, before collision against the wall, which we're going to be focusing on, what happens is that the molecule moves to the wall, creating a specific momentum direction where we have to consider the coordinates. And in here we have the coordinates to be first focusing on the x, which in this case is looking at the momentum m multiplied by the velocity on the x coordinates. And after collision against the wall, we're going to look at how this molecule then moves to the bounces and moves to the other direction. So therefore, after collision against the wall, we actually have our x coordinates to be in the negative direction. Therefore, we have our momentum here to be mvx negative. So since before collision must be actually effective to be equal to also that of after collision, therefore this expression, if you move the other momentum to the other side of the equal sign, we have the absolute value of the momentums, which is actually going to be 2mvx. So therefore, once you're able to combine the momentums, we have the change in momentum to be expressed as that. So since we have this particular assumption being made for the momentum of just one particle or one molecule, we need to take note here in terms of the coordinates that the y and the z components on the linear momentum is actually unchanged as a result of the collision. And this is going to be carried over next to what we know after determining momentum, to the time interval. And the time interval is really crucial because this gives us the volume relationship with the area in a specific space. So therefore, if we have this specific space right here, and this region here is considered to be the wall where the container is actually surfaced, and we have our coordinates in here this our wall based on the coordinate is aligned on the YZ plane, and once we have a molecule that is actually in a specific area that is more likely to hit the wall, this is actually going to be considered versus the other area of that particular space where some region of molecules will less likely hit the wall at a specific time. So therefore, in this case, for the volume, how to determine the volume, all we need to consider is focusing on the ones that are willing to hit the wall, and that region of space where molecules are more likely to hit the wall is going to be represented as that particular distance, which is represented as dx because it's on the x coordinates. Therefore, the dx is taking into consideration the absolute value of the velocity of the particle, specifically that one, and multiplying that by the change in time that is recorded. Therefore, in here, since we know that the area of the wall gives us the YZ coordinate plane, we will be able to determine the volume to be the multiplication of the area and the specific height, or I'll call it the distance covered by that particle moving from that first green line to the wall. Therefore, in this case, once we have our volume relationship between that of time, velocity, and the area that the particle is hitting against, we need to consider how many of these molecules will hit the wall, and how many molecules goes back to the first assumption, which says that random motion is made by gas molecules with mass A. Therefore, this relationship tells us that the number of moles of molecules that are willing to hit the wall is going to be in the ratio with that of the volume of the molecules that are, or moles of that are occupied, that will hit the wall, and this is equal in terms of the ratio to the total number of molecules, total number of moles specifically, divided by the total volume of that particular space in that particular container. Therefore, in here, to solve for number of moles that are willing to hit the wall, we just have to cross multiply, and we get this to be the new expression. And since our volume expression shows us that the will is in the same relationship with the area and that of the velocity and the time, we then incorporate that into that expression, and we get our new expression for the number of moles in terms of not only the area but also the velocity, the time, and that of the volume. So the total volume one considered in here with that of the number of moles that are willing to collide with the wall, we then move on to the next step here, which involves how are we going to incorporate the number of moles to the number of molecules. And this comes into play when dealing with our regular organic regular chemistry, where we talked about the Avogadro's constant, where in this case, since we have this expression determined from our previous slide, we know that since the number of moles that are willing to hit the wall is equal to the ratio of the number of molecules to that of the Avogadro's constant, which is represented as Na, and we know that this is equal to 6.023 times 10 to the power of 23 units. Therefore, we incorporate this particular expression into the previous expression, and we are going to get the number of molecule expression to be equal to the multiplication of the total number of moles and that of the area with the velocity on the x coordinate and the change in time, all divided by the total volume, and all this is multiplied by the Avogadro's constant, and we will be able to determine the number of molecules that will actually hit the wall. So how do we get in here from number of molecules that hits the wall to then momentum? And this is actually taking into consideration an assumption which involves probability. And probability, if we assume in here that half of the number of molecules will in this case hit the wall or collide with the wall, then this particular direction of the molecules are with respect to the positive momentum of those particles. Therefore, since we have a relationship with the number of molecules with that of one particle's direction, which is then incorporated into all the half molecules direction momentum, then we consider that half of that particular number of molecules, which is expressed as half of the total number of moles times the area times the velocity times the change in time divided by the total volume or multiplied by the Avogadro's constant, will actually be for the whole half particles or molecules that we hit the wall. So therefore, in this case, one molecule's momentum, which is expressed as our previous expression for momentum absolute value to be 2 times the mass and the velocity on the x-coordinate, then we can actually determine the momentum of half of the number of molecules that will hit the wall in terms of the momentum. Therefore, in here, once we go into that, we will be able to determine half of the number of molecules that will hit the wall, and this is actually incorporating that expression into the momentum absolute value expression, and this leads into a couple of things actually linking up. We have 2's cancelling out, and we have noting that the relationship between the mass and that of the Avogadro's constant actually leads to the molecular weight of that particular gas or molecule. Therefore, our expression now in terms of momentum is with respect to now the molecular weight of that particular gas that is in that particular space, and this is a product with the total number of moles, and this is multiplied by the area, the velocity squared, and that of the change in time, all divided by the total volume. So therefore, since we have our momentum for half of the particles that will hit the wall, then we have to take into consideration using this particular expression for momentum, which is right here, into the pressure volume relationship, because when there's momentum, half of those molecules moving with that momentum, they create pressure on that particular wall after they collide. So therefore, that pressure that is created is taken into consideration alongside the volume of gases that are actually causing that particular pressure to be exerted on the wall. Therefore, having that relationship established in here, we will be able to take note that looking at the pressure, we know that the pressure is the ratio between the force and the area. Therefore, since we know that the force is the product of the mass and the acceleration, all divided by the area, which is represented as A, we therefore know that our acceleration is the ratio between the velocity and the change in time. Therefore, the numerator, which is m multiplied by v, is related to momentum. Therefore, since we have our change in momentum to be divided by the area times the change in time, this is equal to pressure. And once we have the pressure relationship with momentum, this is awesome because we now have half of the molecule's momentum directly related to pressure. So we have to put this into the pressure expression. Therefore, we are going to arrive at our pressure, which is in terms of the number of moles total, the molecular weight, the area, the velocity, the time, and the volume. And we notice here that the numerator and the denominator has the same variables. Example, we have time that is common and we have acceleration that is common. So once those cancels out, it means here that in total the pressure is independent on the area and the time, which is fascinating. And this actually leads us to the one of many steps that shows the direct relationship between the pressure and the velocity that is really important to establish. So we know that velocity will most likely lead to the molecular speed, but how can we be able to transform that velocity Vx, which is just considering the velocity on the x component, into the molecular speed? And this is where the next step comes into play, where we have determined a reasonable relationship between pressure and velocity, but we need molecular speed. So therefore, in this case, in order to do the molecular speed, we need to perform the root mean square speeds of all the molecules in that particular container. And this will also be including the 3 dimensions in that particular area, where the root mean square will be able to be applied to not only the x, the y, and the z velocity. And if we perform the the mean squares of the x, y, and z, it means here that we're going to make an assumption in here that all of them are equal to each other. So therefore, since in this case that the root mean square speed, which is represented as c, in this case we're going to show that how can we determine the magnitude of that particular root mean square. This means that we're going to perform the root mean square speed all squared is equal to the sum of the average or the mean squares of not only the x, the y's, and the z, but also as a result we actually use the square root to actually determine what c is. So since we made an assumption that all the mean squares are equal to each other, we can then incorporate that into that particular sum expression on the square root, and we will then make the sum to be equal to 3 to the average or the mean square on the x of the velocity. Therefore, performing the square root and solving in here for the v squared on the x average, we will then arrive at this expression which shows relationship between the velocity square on the x mean to be that of the root mean square, which is represented as c. Therefore, in this case, once we have this expression established, we will then incorporate this expression in terms now of the average or mean of the square velocity to the pressure relationship with the velocity on the x coordinate all squared. And once we see that, we're going to take the places of the v x to the power of 2 in place of the c squared over 3. Therefore, once we have this established, therefore we can determine our original goal, which is to determine the direct relationship between pressure and the molecular speed, which in this case is P multiplied by the volume total, and this here is equal to 1/3 of the total number of moles multiplied by the molecular weight and multiplied by the root mean square speed all squared. Therefore, in this case, we have shown the direct relationship between P, which is pressure, and that of the molecular speed, which is represented as the root mean squared speed expressed as c. Therefore, finally, in this particular video, we are able to actually going to introduce the Boyle's law, or some people call it the ideal gas law, which is in this case PV equals nRT. Incorporate that for an ideal gas into our specific pressure to the root mean square or molecular speed expression or equation in here, and this will be used to determine the expression used to determine the root mean square speed of any molecule, mainly ideal gas, when we solve for C, and we actually get C to be equal to the square root or square root of 3 times R, which is gas constant, multiplied ideal gas constant multiplied by temperature divided by the molecular weight. Therefore, in here, since R is the ideal gas constant, we can lead to the conclusion that since C is the root mean square speed of an ideal gas, which is also related to the molecular speed, we can say that the root mean square is directly proportional to the root of the temperature and is inversely proportional to the molecular weight. So as the molecular weight of the gas increases, the root mean square of that particular speed of the gases will decrease, and if you increase the temperature, rightfully so, increase the root mean square speed of that ideal gas. So these are the conclusions that are made based on a specific way to derive not only the relationship between pressure and that of the molecular speed, but also what does the root mean square speed implies in an ideal gas. So that's about it for this particular long video. Hope you're able to understand this. Please hit a comment down below, let me hear your thoughts, but that way I could talk to you soon. Stay smart, believe in yourselves, don't forget to hit the like, share and subscribe, but that way I could talk to you later. Stay blessed.